In this video, we will learn about square roots, cube roots, nth roots, and some vocabulary that goes along with all of these and radicals in general. Let's start with what we know. We looked at perfect squares and square roots yesterday and how they are opposites or inverses of each other. For example, we saw that 5 squared is 5 times 5, or 25. In other words, if you made a square with side lengths 5, we would have 25 square units making up the area of that square, as we can see here. So if I were to take the square root of that and say how long is each side length of that square, I would take the square root of 25, which is 5 times 5, and I would get 5. Yesterday we focused on square roots, but the same principle applies to higher powers. For example, we know that 4 cubed is 64 because 4 times 4 times 4 equals 64. And we could visualize it like this. A cube with its length, width, and height all being 4 units. Therefore, if we're taking the cube root of 4 times 4 times 4, or 4 cubed, we get our root of 4. The same principle is going to apply for higher powers. So we had memorized a few higher powers back in the exponent unit. Let's look at one example. Let's look at the 5th root of 32. Since 32 is 2 times 2 times 2 times 2 times 2, or 2 to the 5th, the 5th root of it undoes that raising it to the 5th power, and we just get 2. We don't have a visual for anything other than squares and cubes because we can't in our brain imagine a 5th dimension. Overall, I highly suggest memorizing this whole list. Imagine trying to do some of the units you've done this year without knowing your multiplication facts. The same efficiency will be felt in this unit. However, you can always refer back to this list if you need it, and it may even be on the inside cover of your notebook if you have one. One of the most important things to remember is that radicals are simply numbers. We can write numbers in many different ways. For example, the number 4 I could write as 8 over 2 if I wanted. Each integer on our number line could be written as a square root. For example, 5 is equivalent to the square root of 25. It's also equivalent to the cube root of 125, or the 4th root of 625, because 5 to the 4th is 625. If I wanted to put a number between these, for example, the square root of 24, that would be a little bit smaller than the square root of 25. So it would be a little bit smaller than 5. Let's talk a little more about the words perfect squares and perfect cubes. 1, 4, 9, 16, and 25 are our first 5 perfect squares. 1, 8, 27, 64, and 125 are our first 4 perfect cubes. What this basically means is that we could make a square with an area of 1 by making it a 1 by 1, an area of 4 by making it a 2 by 2, an area of 9 by making a 3 by 3, etc. And with our cubes, the same logic applies. So let's look at the highest one. We have 5 by 5 by 5 for our dimensions of our perfect cube. This also means that we can take the square root of any of our perfect squares and end up with an integer. In fact, we'll end up with a whole number, which is 1, 2, 3, 4, 5, 6, etc. If we take the cube root of any of our perfect cubes, we'll also end up with a whole number. What happens if we try to make a square with an area that isn't a perfect square, or a number that we don't have a square root of to give us the side length? It's a little hard to see, but when you make a square that has an area of 1, or 4, or 9, are perfect squares, the side lengths are integers. But when you try to make a square with an area of 8, for example, we can see that the side lengths are actually decimals, and they come out as really messy decimals that never end, called irrational numbers. These will never end and never repeat consistently. So by definition, a perfect square is a number that is an integer squared. So if we take the square root of a perfect square, we'll get a whole number. In other words, the square root of a perfect square is rational. For example, the square root of 9 is 3. If we have a square made up of an area of 9 square units, then each side length is 3. The square root of 25 is 5. If we take the square root of something that is not a perfect square, such as the square root of 8 or the square root of 20, we get a non-terminating decimal. That means that if this calculator went on for a few more feet, those decimals would keep going on without repeating for a few more feet. This gives us an irrational number. This may feel overwhelming and like a lot of information at once, but it's important that you learn the words and understand the language so that when you speak about it, you can speak with more precise language, and when I teach, you can better understand the concepts. So let's take some notes together. The first thing is understanding the different parts of a radical. We often are working with square roots, but this whole thing is our radical. We have an index that tells us if we're taking a square root, a cube root, a fourth root, a fifth root, etc. We have the radicand, which is the part inside of the radical symbol, and it tells us what we're taking the root of. If there's no index written, it's implied that it's a 2, which tells us that we're taking a square root. I'll show you what I mean in our first example. So what it's asking, a square root is saying that 2 factors of what number equals the number inside, or what number times itself equals the number inside. So the square root of 100 is 10. In this case, we're taking a square root, and we know that because no index is written, so it's implied that it's a square root. It's saying what number squared equals 100. 100 is our radicand, and if we were to simplify it, we would get 10. You could probably list a bunch of other square roots here. So I listed 2 for you. The square root of 49 is 7 because 7 squared is 49. The radicand is 49. The index is 2 because that tells me that I'm taking a square root and it's implied. Then we have nth roots, which is just the more general case. We might be taking a cube root, so the cube root of 125 is 5 because 5 cubed equals 125. Or we may be taking a fourth root. The fourth root of 16 is 2 because 2 to the fourth is 16. So we know that our radicals are the opposite of our exponents. Whenever you're learning something new, it's important that you read it, write it, speak it, and listen, whether it's math, a foreign language, or anything at all. So I'm going to first go through this chart aloud, and then I'll fill it in, and you can pause it to copy it onto your paper. The first expression is the square root of 49. This simplifies to 7 because 7 squared is 49. We say it out loud, as I just did, as the square root of 49. Its index is 2, and its radicand is 49. Then we have the square root of 25. This simplifies to 5. Its index is 2, which is an optional thing to write in, and its radicand is 25. We have the cube root of 27x cubed. This simplifies to 3x because that is the expression that we would have to cube in order to get 27x cubed. Then we have the fourth root of 16, which we saw on the previous slide, and since 2 to the fourth is 16, the fourth root of 16 is 2. And finally, we have 4 times the square root of 36. We often read this as 4 root 6. You can read it with a shortcut as long as it's a square root. This simplifies to 24 because we have 4 times 6, which is 24. Pause the video and copy this into your notes. If your notes aren't exactly the same, use your logic to fill in the ones you don't know, and you can always get them checked by a teacher or a peer. Notice that I wrote out a little bit of the work to remind you that since we were taking the cube root of 3x cubed, that's why we ended up with 3x. The cubed and the cube root canceled each other out. Remember also to practice saying these aloud because it is important to do all 4 of these things at the top of your screen. So to summarize, our perfect squares are numbers whose square root values are integers. So we have 1, 4, 9, 25. We could jump up to 100, 121, etc. If you picture your multiplication chart, it's these green numbers that are going diagonally down the middle. The radical is the symbol for the square root, and the radicand is what's inside that radical symbol. And finally, irrational numbers are numbers that cannot be written as a fraction, do not repeat or terminate. Anytime we're taking a square root that does not simplify to an integer, it's an irrational number. So the square root of 2, the square root of 3, the square root of 4 would be 2, so that's not irrational. Square root of 5, those are all irrational. And if you think higher, the cube root of 2, that would be irrational because we cannot take a number and cube it to get 2. I know that this is a lot of new vocabulary and a lot of new information talking about what it means to be a perfect square, a radicand, a radical symbol, a square root in general. But it's important that you understand these words and these concepts before we move into the unit where we will be simplifying, estimating, and solving using radicals, mostly square roots and some cube roots. But just think, now there are a whole world of math comics that you can understand.